Good morning and welcome back. So, we are going to continue the results. So, last class we are discussing the general second order equation, this LU equal to F without even the assumption of A naught is non negative, and then you have small a, AUV is this form what you have written here, and as I said, A need not be elliptic, and we are going to state a general theorem where we will be applying the Fredholm alternative. Okay. So, we have to understand the homogeneous equation. So, that is what we are going to study. When f equal to 0, that is the okay, the set of, so let me give us some number here. So, maybe this I will call it 1. So, this weak formulation I will call it to 2 always, the strong form is 1, weak form is 1. When f equal to 0, the set of solutions of 2 form a, that is what we want to see, form a finite dimensional subspace of H1 naught, you see, you call it say of dimension D, okay, D, okay. Moreover, there exists a finite dimensional subspace which is nothing but the solutions of the adjoint equation. Some dimensional subspace f of H1 naught of omega of dimension D such that 2 as a solution has a solution for a given f in L2 of omega if and only if f is in the orthogonal, the perp of f perp, okay, the orthogonality of f perp. So, note that we do not assume A naught greater than or equal to 0. So, let me try to give a proof of this. Okay. So, I want to give a proof, probably in, so mark it here. So, I want to give a proof. So, the first step is that the first claim, I add a large zeroth order term, claim there exists lambda positive, such that AUV plus lambda integral of UV is H1 naught elliptic. You see, AUV need not be H1 naught elliptic, but you can choose a lambda positive. So, you can put a very heavy first order term to prove that this bilinear form, your BUV equal to AUV plus lambda UV is H1 naught elliptic. So, what you do is that you know that A naught and A naught. So, the first step is the proof of this claim, that is fine. So, choose lambda positive because this A naught are C infinity function such that A naught of x plus a lambda, you can add a large enough lambda. So, this is away from 0, A naught need not be, but it is in L infinity. So, you can put a positive quantity bigger than that. So, this should be greater than or equal to some gamma positive, this you can do that one. So, now so so how do you prove that one? So, then what is BUU? BUU is equal to AUU plus lambda integral of u square. So, this can be now estimated. So, you recall this estimate. So, what is this AUU? Integral of Aij. So, let me not write all the time, du by dxj du by dxi plus Ai du by dxi what is and du by dxi u plus A naught plus lambda, I put it together, A naught lambda integral of u square. See. So, by ellipticity, this you can write it as alpha into grade u square, you get that one. Here this is a is a bounded quantity. So, what you can do is that this can be estimated, the modulus of that can be estimated some beta into grade u into u, you see, you can do that, you can estimate. So, I can put a negative of that one from, so this can be estimated by that one. So, this can be estimated that one, and this is greater than or equal to gamma. So, this is greater than or equal to gamma. So, that gives you minus beta grade u in norm u plus gamma norm u square. So, you have this. Now, I want to square this in the sense that you have alpha minus, let me do properly. So, you have your alpha into grade u, alpha grade u square and plus I make a squaring thing root u norm of u minus beta by 2 root gamma norm of grade u square, and then you will get a positive quantity that has to be removed, beta square by 4 gamma into, sorry, this is 2 is not there, the 2 will be here, and this takes care of the second and third term, and then you have to remove that term, norm of grade u square. Okay. So, with that, this is a positive quantity. So, you see, this is a positive quantity. So, this is greater than or equal to 0. Now, that will be greater than or equal to alpha minus beta square by 4 gamma into norm of grade u square. This is what you want to do it. Now, look at the gamma. Gamma is choice from here. So, I can make if lambda much bigger, so that you can choose gamma large enough. So, choose large enough so that gamma is large enough, such that alpha minus beta square by 4 gamma, because gamma is large, this can be made small. So, this can be greater than 0. So, that implies your BUU is greater than or equal to some constant alpha bar into norm grade U square. Now, apply Poincare inequality to get it some other alpha, maybe tilde into norm of U at H1 naught omega square. Okay. So, that gives you, so that implies, so you have a weak formulation that implies, okay. So, this is there. So, apply Lax-Milgram, there exists a unique U, not about the solution to our problem, there exists omega such that AUV plus lambda integral of UV equal to integral of FV for all V in H1 naught. So, that you have it. So, how do we proceed further? So, we have a solution operator. So, let us go to a solution operator. Solution operator. So, what is the solution operator? You have F in L2 of omega, okay. That gives you a solution H1 naught, and we call this is the mapping G. So, G is what is G? GF is equal to U, solution of the previous solution of AGF, that is your solution AGF V plus lambda integral of GF V equal to integral of FV. So, that is what you get it, a solution operator. Now, H1 naught, so you have a mapping G which is from L2 to H1 naught, continuous at this stage, and this is compactly contained in L2 of omega. So, you can view your G from, this is compact. So, you can view the solution operator not just from L2 to H1 naught, but you can view that operators from L2 to L2, in that case which is compact. So, this is where you are using the first time you are seeing the compact embedding, you do that way. Now, so this let me call it star, I do not know what number I given. So, you have a thing. So, now look at it, if look at this, observe this now, this is the important observation immediately. U is a solution of, this is what if U is a solution of AUV equal to FE, this is what you are looking at it, right. If and only if, take this term to the right side, U then equal to G of F plus lambda U, an implicit operator form. So, if you take this to here right side, if you take this right, this will be F plus lambda GF. Okay. So, that is GF is so if U is a solution to this one, if and only if this satisfies, this is what you get it. Okay. So, put now V is equal to, so I am just putting in the form which I want, the operator form F plus lambda U, then your star double star. So, star is not star is equal to double star, this one. Okay. So, this is our solution, this, okay, F plus lambda V, that will imply your V minus lambda GV equal to F, or in a typical form if you want it 1 over lambda v minus gv equal to 1 over lambda f. That is okay, does not matter where you get it. This is a typical form of this one if you recall, okay, Tx minus lambda x, where g is a compact operator. So that is it. So that immediately proves. So this implies, so if lambda, so now two cases. If lambda, because lambda coming here, if lambda should come here, okay. If lambda inverse is not an eigenvalue, value of g, then that implies there exists a unique solution. This is the case d equal to 0. That means you have a solution for everything. This is the case where you get d equal to 0. Okay. If lambda inverse is an eigenvalue, then it is the then the result follows by Fredholm alternative. What does that mean? What does that means that it has lambda inverse has finite multiplicity. Has finite multiplicity. That's what it proves. Okay. In other words, okay, the corresponding and the finite dimensional space stated in this theorem is precisely that finite dimension. So the homogeneous equation has thing, and the thing and solution and equivalently solution. This is the homogeneous equation. So the finite multiplicity is the solution of some the adjoint equation corresponding to that one. Now the solution for f in L2 of omega exists if and only if, so there exists finite dimensional space. Okay, that also gives you a finite dimensional space if and only if f is in that kernel of I minus lambda g star perp, which has the same dimension, that you know, which has the same dimension. So that is a very good application of your Fredholm alternative. So I just want to make some remark. It is not really a remark, a result. I do not remember whose result it is, but probably you can see the Gilbert and Trudinger, or probably maybe there also in the new book of Brazis, functional analysis of low spaces and PDE. It says that so as I say that if you can show that d equal to 0, then there is a unique solution. That is a thing. So using maximum principle, even in this general case, if A naught is greater than or equal to 0, one can show that d equal to 0. That means you do not need conditions on AI, can show that d equal to 0. Do not require This is what I said, the zeroth order terms is the one which creates trouble. Do not require any other condition, because of course you need AI to be smooth and L infinity functions and other condition, but you do not need any sign condition, do not require any other condition on AI. Okay. So you can so the next step is, so what we have discussed about the value about the equations, PDE elliptic equations with the Dirichlet boundary conditions. Now let us go to Neumann condition. So let us with the Neumann condition, I will do it for the Laplacian. Of course you can also work out with the general equation, general L0 equation. Okay, Neumann condition. So let me do some results with the Neumann. So look at this equation. So let me a case, easy case. That is a slightly difficult case when you do not have the zeroth order term. Okay. So you consider this equation f in L omega and du by d nu equal to 0 on d omega. Okay. So this is a simple exercise. So this is your first equation. You have this exercise is slightly maybe more how to derive it. So I may skip tell few things how to get back. It's one is a weak solution exercise. Get a weak formulation, get the weak formulation. Now you cannot work with h1 naught of omega because u is no longer 0. So you are looking for du by d nu equal to 0. So you have to work with you have to work weak formulation. So that is the first step you understand. Weak formulation u in h1 of omega with grade u, integral of grade u, grade v plus uv. The idea of adding, if you do not add the zeroth order term, there are troubles. Okay. And so, and this also Poincare inequality is not true in h1 omega space for all v in h1. This you can immediately get it, that is not a problem. Going back is little more issues which you have to understand, but you fill up the steps which I am doing it here. Okay. All right. So, and what is the prove existence uniqueness? Okay. So, maybe I will illustrate. The exercise is use Lax-Milgram lemma, use Lax-Milgram to prove well-posedness. I write well-posedness means existence uniqueness and estimate, and this estimate you have to prove h1 is less than or equal to constant norm u. But this is more easy in the sense that there is no Poincare inequality, but and you do not require Poincare inequality because of that. So it is exactly the norm, so which you are proving that one. So how do you go back? So assume 2, that is what you want to show, right? Assume 2 and take u is in and take u in h2 of omega. Once you do h2 of omega, you can do an integration by parts here, integration by parts, because u is in h2 implies Laplacian of u is in L2 already. Integration by parts, or you take u is in C2 of omega bar, you can take that also to start with. So integration by parts, when you are doing an integration by parts, you get minus Laplacian of u v, this is in omega, and then you will have a term here, integral of d omega du by d nu v over d sigma plus integral over uv equal to integral of f. So, you see this is what you will get it, because the boundary term has not gone yet there, and this is true for all v in h1 of omega. Okay. Since it is true for all v in h1 omega, the above equality is true for all v in d omega, which we have done earlier also. That is, once you have for all v in so you see, when you take a v in d omega, this term will disappear. That means you get that. So, that is integral of, you get minus Laplacian of u plus u minus f v over omega, only now not for all v in h1 of omega, this for all v in. So, these are the small subtleties when you work with weak formulation. So, to be very careful with the subtleties. Okay. Now, this is true for earlier you got it with h1 naught, but then the boundary condition gives only when you take v in d omega. So, this is in the sense of that implies minus Laplacian of u plus u equal to f in distribution. That is the meaning of a distribution, and that is the first step you want it. And since u is in, you get something more now. Since v is in d omega, you see this is the way you have to for a thing another, which is dense in this d omega is dense in L2 of omega. Okay. Once this is L2 of omega, you get this minus Laplacian of u plus u minus f equal to 0 in the sense of L2 of omega. The meaning of that, you have this minus Laplacian of u plus u minus f equal to 0 for all v in L2 of omega. In particular for all v in h1 of omega. You see the way you derive. Of course, so this implies in L2 of omega, so I will come back to that one. This also implies minus Laplacian of u plus u equal to f almost everywhere. If you further, if u is in C2 of omega bar, implies minus Laplacian of u plus u. Of course, you need f is also in C omega, C2 of omega, C omega implies pointwise. That means u is classical. You got that one. What about the boundary condition? So, this way you can do little more exercise from here. Since now you got these things, for v in h1 of omega, this will imply you integral du by d nu. You do an integration by parts at this stage. From this integration by parts, you get v equal to over boundary of omega equal to 0 for all v in h1 of omega. Okay. And that is the meaning when v is in h1 of omega. So, one way to think that v is in h half of omega, so that u is in h1 of omega, that is a solution you have done. So, you can interpret u by d nu, which in the thing you can interpret it as an h minus half of omega d omega. You see, and this is precisely you can interpret it as the duality between, if V is in L2 and you have U is in H2, you will get it as H half. In that case you get L2. So, depending on further regularity you can get more. So, this is basically H half. So, this will be H minus half, that equal to 0. That means du by d nu in the general K is equal to 0 on gamma wherever it is. So, you can interpret that way. So, you can try all these things here. So, I more or less stop here. So, what I am going to do in the next class, we consider this equation without the first order term. Okay. We will do the case with the minus Laplacian of u equal to f in omega and du by d nu equal to 0 on d omega. You see, immediately you can observe u equal to constant. If u is a solution, u plus c is a solution. So, solution is not unique. You can also see that there doesn't. So, there is no existence and uniqueness immediately unless you put additional conditions, okay, which we will discuss in the next class. Thank you very much.